So at this point, they know that if you take a coil of wire, right, and you run a current through it, right, this is Ampere's law, right? That's supposed to be a coil, right? If we run a current through this, right, okay, and it comes out this way, that we get a nice magnetic field. The magnetic field comes out here and does this, right? Okay, so the question was, is there a way to make a magnetic field create a current, right? So what they did was they made a coil of wire, and then they surrounded it with another bigger coil of wire. I'm sorry about this picture, right? And they sent current through this outer coil to see if if you send a current through a coil, it creates a magnetic field. So if you put a coil in a magnetic field, does that make a current flow? Right? Well, yes and no. Okay, it turns out that it's only when the when the magnetic field is changing that the current flows, right? And it took them a little while to figure this out. I've got a demo of this, but it's the changing magnetic fields that matter. Okay. Now, on further inspection, they came up with a really good theory of this, right? It has to do with the strength of the magnetic field, has to do with the area of the coil of wire, right? And then there's a little bit of an angle going on there. Let's see if I can explain that, right? So the first concept is the concept of magnetic flux. It's when the flux changes that you get an induced current, okay? So let's imagine that we've got this area right here, okay? Let's also imagine that we've got a magnetic field that's this way, right? Okay, so these lines represent the magnetic field, okay? So if that's the magnetic field, and here's the area, area in physics is represented by a vector that's perpendicular to the surface, okay, and is the length of the vector is proportional to the size of this area, okay. So notice that the angle between the magnetic field and the area, in this case, in that strange way of saying it, is actually 0, okay. And at 0 degrees, the cosine of 0 is 1. Okay, so this is the maximum flux, right? It's a bit like we can think of it if this is a solar panel, right? Intuitively, you want the light shining just perpendicular straight onto that surface. And if we rotated that surface just slightly, that the solar panel wouldn't work as well. I think intuitively we know that. That is solar flux. This is magnetic flux. Okay, so there, flux is a concept of the amount of beams of light shining through, the amount of magnetic field shining through this loop. Okay, now if we change that in any way, then we get an induced current. If this is a loop of wire, we'll get an induced current, right? So obviously, one way to change it is we can have more magnetic field, right? Stronger field, right? The field can just change, right? We could also change this area, right? Now, maybe we don't change the area of the loop, but we could change, maybe the magnetic field is here, right? And we can move this loop into that magnetic field, right? So we could change the amount of area that is in the magnetic field. We could change the magnetic field. We could also rotate this thing, right? If we rotate that, let's imagine that the magnetic field is now this way, right? Well, I'm doing a really good job. Okay, well now the angle is different, right? We've got a different amount of flux. It's no longer 0, it's, 30 degrees or something like that, right? So we could change that, right? And this is what alternators do. Alternators just spin loops inside magnetic fields, right? And then you could change any combination, right? So ultimately, we could change the magnetic field, the area, and the angle. I've never written a problem like that, but you could, right? So basically, think this way, BA cos theta minus BA cos theta. That is your change in flux, okay? So if you change the flux, then you will induce a current in this loop, okay? And I'll try to make a video with the overhead like that. All right, so and then the final thing is that if this is a loop of wire, okay, Lenz's law says that the induced current resists the change in flux. That always works. If they talk about a magnet moving, sometimes you can use the motion of the magnet. It will always oppose the motion of the magnet, okay? So in this case, the North Pole is approaching, right? So the current's going to flow actually down the front of this, if this is a solenoid, not a bunch of circles, right? Okay, it's actually going to flow down the front of that and make this a North Pole, and that will exert a force this way, okay? And the reason for that is actually conservation of energy, okay? If you think about this, as I move this magnet this way, I'm inducing a current in this. If this is actually a coil, I could light up a little light bulb, whoop, right? I could light up a light bulb, I could run a motor, okay? And so therefore it must be that there's some resistance to this motion, because you can't get energy for nothing. You must get that energy from doing work. We must have to exert a force times the distance on this magnet to get work at this end. Energy is work, right? Okay. It's not possible for this to be a south pole, because then it'd be sucking the magnet in and generating energy. That would be like a perpetual motion machine. Okay. So ultimately, it's conservation of energy. Lenz's law is conservation of energy. That the induced current flows in this thing in such a way as to resist the motion that caused the change in flux, or even the change in flux. Okay. Because magnetic fields are also energy. All right. So this is actually Faraday's law right here. Okay, finally we've gotten to it. Okay, obviously you have to explain flux, okay, to explain Faraday's law, because Faraday's law states that the induced EMF, by the way, this is like voltage. Okay, just think voltage. Okay, and there is a difference. So when you go to college, pay careful attention. I kept asking my professor what the difference between EMF and voltage was, and there was something, but it seemed like a word game to me. So if we divide this EMF by resistance, we get current. So anyway. But you'll go study college and come back and explain the difference between EMF and voltage to me. Okay. So electromotive force, or voltage, right? And then this is the number of windings. So if I've got one winding, right, and I've got a magnet, right? N is 1, and then I could have 2. Now N is 2, right? And then I could have 3 windings, right? Every winding is going to have this change in magnetic flux over time, right? And so just the number of windings like that, right? So this is the number of windings that you have. That's the change in magnetic flux, right? That's the time elapsed. Now, ultimately, this ends up being NBA, right? Because this is, right? And then you could have cos theta minus NBA cos theta over the time, right? Okay. Now, a lot of times, right, there's no, like one of these situations is 0, so it's just NBA cos theta over T, okay, is what it ends up being. And we'll do an example here, okay? Okay, yeah, Faraday's law. There it is. This is one of Maxwell's laws, by the way, ultimately. So here's a Faraday's law example, okay? So we've got this loop of wire. Now keep in mind that if I move this loop this way, there's no change in flux. If I move it this way, there's no immediate change in flux, right? If I move it this way, even for just a little bit of time, there's no change in flux. But as soon as this loop starts to leave this area here where the magnetic field is, okay, then there is a change in flux. So these dots represent magnetic field out of the page, right? Right? And as soon as this loop starts to leave that area, then we have a change in flux. Then we have a situation where there's an induced EMF. Okay, so let's take a look at this thing, right? We've got 75 centimeters, 50 centimeters. Well, by the way, if I rotate the loop, we would get an induced flux, right? But as long as it's square with the field like this, right, and we just move it around inside the field, no flux. But as soon as it starts to leave, right, then it's going to be minus N change in flux over time, right? Right, which ultimately EMF is equal to N and then B times area. The angle here is actually 0 degrees because the area vector is pointing straight out of the page, we'll just say. Okay, and then over the time, right? So this is going to equal, there's one winding here. Let's assume that there's one winding. So N is 1. The magnetic field is 1.7 Teslas, which is a lot of magnetic field there. And then my area goes from all of the area to none of the area, right? 0.50 times 0.75. And I know that, by the way, there's a minus sign here. I'm just sort of ignoring that because, I mean, I know there's probably a way to cleverly do this, but I'm not that smart. Okay, so we're going to figure out the direction not by using the minus sign. I'll just put a little parenthesis there, right? Okay, I'm not going to use the minus sign to find the direction that it goes. I'm just going to I'm going to use my brain. All right, so basically this calculation is very simple. So NBA over T, National Basketball Association. Okay, so 1 times 1.7 times 0.5 times 0.75 divided by 0.012. 53.125 volts. How many sig figs? We only have 2 sig figs, so about 53 volts. Did I do that right? I feel like I did. Let me see. Yeah, there it is. All right. Now, which way does the current flow? Well, don't you see? Let's figure this out, right? We have flux out of the page. So what's happening is we're losing flux out of the page. Right? So that's the first step, is you got to figure out what's happening, right? We are losing flux. And the reason is that we had the flux and we're pulling this thing out of there, right? And so we no longer have it, okay? So we're losing flux out of the page, right? So if we lose it, we replace it. So how do we replace flux out of the page? The current is going to flow in such a way to replace flux out of the page, right? Okay, well, take your right hand, okay? The current has to go anti-clockwise to create flux out of the page, right? So if the current is anti-clockwise, that creates flux out of the page, right? Yeah, so anti-clockwise, the current flows anti-clockwise. We'll practice some of those in class. Sometimes I think it's hard to do that in a video, but anyway, take a look at the next set of problems here.